Hi class, welcome to the lecture on the chapter 10 odds problems. Let's remember the title of the chapter is the t-test for two independent samples. We'll go and begin with question number 1, which reads, describe the basic characteristics of an independent measures or between subjects research study. Okay, so let's just remember basically what they're asking about here is the type of study that we're conducting in chapter 10. We should begin by remembering that the type of statistic that we're running is the t-test. We've been learning about this type of statistic since about chapter 8. In chapter 10, we're just learning how to do it with this thing called the two independent samples. Let's remember that in the chapter 10 lecture notes, I covered that in this part right here, right, where we're basically describing what this independent measures design looks like. So let's just go ahead and answer the question, just to kind of remind ourselves what this is all about. The way that I want you to kind of realize the way that we're answering the question is we are talking about these basic characteristics of this type of design, the two independent samples. Here they're referring to it as an independent measures, right? That's another way that you can talk about it. Or another way that you can refer to it or name it is you can also refer to it as a between subjects design. Okay, so let's just remember that what you're doing in this type of study is you're using two separate samples in the study, right? Remember, a sample is some group of participants that you've collected from some population, and you're using the sample to represent that population. So here we're saying that there are two different ways that you could use these separate samples in the two independent samples studies. You could use the separate samples for each treatment in an experiment that you conduct. When I talk about this in the lecture notes, I refer to each treatment as two conditions. We should note that you can use those two terms synonymously, treatments and conditions. They basically mean the same thing, right? A condition or a treatment is the thing that you're doing to your participants. Okay, so here I'm calling it a treatment. The example could be that for one of the samples that you've collected, they're going to get exposed to the independent variable, right? The thing that you're doing, that treatment. The other sample, on the other hand, your sample 2, may be the group that's not going to get exposed to the independent variable. They may get some kind of placebo instead. Okay, so that's one way that you can conduct the independent measures t-test. A second way that you can do it is you could also, right, or you can compare different populations to each other. Let's say that the example that I have here is you're going to collect two groups of participants, right, a sample 1 and a sample 2. And you may do the same thing to the two groups, right? Sample 1 will get exposed to the IV, and sample 2 will get exposed to the IV. The difference between the two samples is they're each going to come from a separate population. Maybe sample 1 could be a group of people that come from a population of men, right? And your sample 2 could be a group that comes from the population of women. Okay, so that's what we mean when we talk about the basic characteristics of the independent measures t-test or the between subjects design. From there, I'll just kind of give you a hint about what question 2 is asking about. Here it's saying that they want you to describe what's measured by the estimated standard error in the bottom of the independent measures t-statistic. So let's just remember that that's this new t-statistic equation that you're doing. Maybe one way that we think about it is we go back to the idea that with this t-statistic, you are conducting that hypothesis test, right, where you're running through the 4 different steps. Your first step was where you're articulating what your two hypotheses are your null and your alternative. Your step 2 is where you're finding your critical region. And step 3 is where you're calculating this series of 3 different equations, right? And the reason why you're doing this is to get some kind of t value. So let's just remember that in this chapter, right, in chapter 10, the series of equations is first you're going to calculate that thing called the pooled variance. Once you have that, then you're going to calculate this thing called the estimated standard error. Once you have that, then you're going to use it to calculate t. What were the equations for the three different values? Remember that's this one here, the pooled variance, is your sum of squares 1 plus your sum of squares 2 divided by your degrees of freedom 1 plus degrees of freedom 2, right? So that's your information from your first sample, and then this is information from the second sample. Once you've used this information to calculate your pooled variance, then you'll use that pooled variance to calculate your estimated standard error, which was this, right? So here's my symbol for estimated standard error. The equation for it is the pooled variance that I've calculated here. Now under the square root, where it's going to be pooled variance over the n of the first sample, and that being added to the pooled variance of the n of the second sample. Remember that once you've got this, right, this estimated standard error, you're then going to use it in your t equation, and that's what you're solving for, this value of t. Remember the way that the t equation looks is now your estimated standard error is your denominator of your equation. The numerator is where you're taking your two samples and you're subtracting the means of the two samples from each other, and that's being subtracted from the two population means. Remember the way this is supposed to work is that in this equation, this is supposed to equal 0, right? So when you actually go to carry out the equation, you're not going to worry about any of this stuff since that's 0, right? It's ending up being this minus that 0, so you can just disregard all this stuff. So when we go to calculate t, it's just going to be this over this. Okay, so that was a long, big drawn-out explanation answering this question. Let's just remember that the estimated standard error is the second thing that you're going to calculate inside of your step 3. What is it? It's recognized with this symbol. This is the formula for it, and this is the definition for what it is here. It's where you're combining the errors for the two sample means. Okay, so that's your answer to question number 2. Let's go and move on to question number 3. Here we're saying, first I'll read the question to you guys. It says that one sample has a sum of squares of 36, and a second sample has a sum of squares of 18, right? So some researchers got 2 different samples and got these results when they did something to the participants. Question A is asking, if n equals 4 for both samples, find each of the sample variances and compute the pooled variance. Then once you've done those 2 things, then you're supposed to find this. Let's just kind of focus in on this first sentence real quick though. Right, here's where your instructions are. You've been given this sum of squares, that sum of squares, and told that for both groups their n is 4. Now you're supposed to find each of those groups' sample variances and then find the pooled variance for those 2 different groups. Okay, so how do we go about doing that? Let's remember that your equation for sample variance, right? Remember, this is your symbol for sample variance, and the equation is sum of squares over degrees of freedom, right? And we just went over what the pooled variance equation was. I'll just kind of remind you. Remember, that's your symbol for pooled variance. The equation for it is sum of squares 1 plus sum of squares 2 over degrees of freedom 1 plus degrees of freedom 2. Okay, so first we'll find sample variance, then we'll find pooled variance. Remember that when we go to do this, we have to find the sample variance for each one of our groups, right? The sample variance for this group and the sample variance for that group. So the way I'm going to do that is I'm going to start off by calculating the sample variance for the two different groups. Right, so for the first group, the sum of squares was 36, their n was 4. That gives me the information that I need to calculate the sample variance for that first group. The way the equation is going to look is, right, sum of squares over degrees of freedom, so 36 over 3. And that's going to give me, for that first group, a sample variance of 12. Before I move on from question A, though, I have to calculate the sample variance for the second group as well, right? So now it's going to be sum of squares of 18 over degrees of freedom of 3. Why degrees of freedom of 3? Because we have an n of 4 over here. So for the second group, that gives me a sample variance of 6. Maybe one way to just kind of know that we're dealing with these two different sample variances. So we can say that this is sample variance subscript 1 and sample variance subscript 2, right? So that's the variance for the first group and the variance for the second group. From there, we were supposed to then use those sample variances to find the pooled variance. And that's what I'm doing down here, right? So, right, remember now our symbol for pooled variance is your sample variance with that subscript P. Remember, its formula is the sum of squares of the first group plus the sum of squares of the second group over the degrees of freedom for the first group and the degrees of freedom for the second group. That gives us 54 over 6, which then gives us a pooled variance of 9. Okay, so then we want to notice what they're saying in the second sentence about this data that we've got here, right? They're saying, because the samples are the same size, right, both are an n of 4, you should find that the pooled variance is exactly halfway between the two sample variances. And we do find that here, right? So here's one sample variance, here's the other sample variance, here's the pooled variance. It is right in the middle of our two variances. Right, so that statement ends up being true. Let's go ahead and move on to question B now. It says, now assume that n equals 4 for the first sample and n equals 7 for the second sample. Again, calculate the two sample variances, right? So we're going to get the s squareds again. That's that right there. And the pooled variance, and so then that's going to be then that pooled variance. Okay, find, here, once we found it, then we're going to say that we've got something that we should notice. But let's go and do the calculation real quick. I've got it right here, right? So our first sample had a sum of squares of 36 with an n of 4. Second sample had a sum of squares of 18 with an n of 7. So that means that for the first sample, I'll just call it sample variance 1 is 36 over 3, which gives us a sample variance of 12. And then for the second sample, it is 18 over 6, which gives us a variance of 3. So then when we go to calculate our pool variance, right, it's our sum of squares of 36 plus the sum of squares of 18 over 3 plus 6 gives us 54 over 9, which is 6. Okay, so now what do we want to notice about our two variances in relationship to our pooled variance? Here what they're saying this time is that you should find that the pooled variance, right, this right here, is closer to the variance for the larger sample. Which of these two variances has the larger sample? This has the larger sample, right? It had n of 7 versus n of 4. So what this is saying is that the pooled variance should be closer to here because that's larger sample. Is that true? Yes, that is true. 6 is closer to 3, then 6 is close to 12. Okay, so really interesting, but we'll go ahead and move on to the next question from there. Here's a quick look at question number 4 real fast. Just kind of note what's going on here. Looks like it's pretty much the same question as you had for question 3. Right, once again, you're being asked to take your two sum of squares, use them to calculate your sample variance and then your pooled variance, and then you're being asked to do it again in question 2, where now the two ends are different. So I'm going to go ahead and move on from that question then, and we'll see. I'll move on to question number 5. And let me get my little cover here. Let's say that for question number 5, the question reads this time: 2 separate samples, each with n equals 15 individuals, receive different treatments. After treatment, the first sample has a sum of squares of 1,740, and the second has a sum of squares of 1,620. Find the pooled variance for the 2 samples, right? So that's question A. Find the pooled variance. So we just did in question number 3. So we should be able to do it easily here. Once we've found the pooled variance, then we're supposed to go find, in question B, we're supposed to find the estimated standard error. Then in question C, if the sample mean is an 8-point difference, is this enough to reject the null hypothesis and conclude that there is a significant difference? So with question C, what basically asking now is for the t-test, right? Okay, so let's say that for question A, they're asking for the pooled variance. For question B, they're asking for the estimate of the standard error, which looks like that. And then for question C, they're then asking us to do the t-test. Okay, so how do we go about doing this? First, we go find our pooled variance for question A. Let's just note that we've got a sample here and a sample here. The information that we've been given about them is some squares and the n for each group. So we use that information to go calculate our pooled variance. We have that right here, right? So pooled variance, that's that symbol right there, equals sum of squares 1, right? Plus sum of squares 2 over the degrees of freedom for your first group and the degrees of freedom for your second group. That ends up giving us this fraction, which gives us a pooled variance of then 120. From there, we're going to go ahead and move on to question B. Right now, in question B, we're being asked to calculate estimated standard error, which is that symbol or this symbol here. Its formula, remember now, is where you're taking your pooled variances, creating 2 different fractions. Each you have one pooled variance. It's going to go over your n for your first group and your n for your second group, and that's all going to be added and then under a square root. So as that problem looked then, it is 120, right? Because that's your pooled variance over here, over 15. Why 15? Because that's your n, plus 120 over 15, because it's the n for the other group as well. Gives you a problem that is the square root of 8 plus 8, which then is the square root of 16, which then is a answer of 4. From there, you can take that 4 and you're going to use it to now calculate t, right? So we go to our C equation. We're saying that for t, we know what the numerator is, right? It's always that x bar 1 minus x bar 2. And the question they gave us with that differences, they said it's 8. So that's why I was able to write 8 over here. Where am I getting this 4 from? I'm getting this 4 from over here. So then it becomes a situation where we're saying our t is equal to 2. Remember what we have to do here though, right? They're asking if the sample mean difference is 8 points, is this enough to reject the null hypothesis and conclude that there is a significant difference for a two-tailed test at a 0.05 level? With this, remember what we have to do is go to our step 2 of our hypothesis test and find that critical region. Remember the way that we do it here is we say it's our degrees of freedom, which in this case was 28. How am I getting that 28? getting 28 because it's 15 minus 1 plus 15 minus 1, right? The two n's minus 1. So that's 14 plus 14 gives us 28. Now what I do from there is I then notice what my alpha level is and how many tails I'm running. I use that information to look up the value on my t-table. Right, so we're saying that I ran it at a two-tailed 0.05 level. So go to my two-tail row, find my 0.05, and look for that value inside the table that corresponds to 28, and that's 2.048. Right, so we're saying in our C answer here is we've just calculated T, it's 2, and we're trying to decide, is this treatment significant or is it not significant, right? That's your step 4 over here. Remember, the base of the decision is you're going to decide that your treatment was significant if this T is greater than this critical value, right? We do find that the T this time is less than their critical value, right? 2 is less than 2.048. So we have to conclude that we're going to accept the null hypothesis and that there is no significant effect. Okay, so the thing that you guys want to notice with question number 5 is they took the steps out of order, but they basically conducted a hypothesis test. Really what they did, though, in this was they really just conducted like steps 3 and 4 of the hypothesis test. How is that the case? That you calculate the pooled variance, then the estimated standard error, then T. Right? It's all these steps in step 3. And then in step C, they asked you to decide, well, is this treatment significant or not? That's your step 4 here. Okay, so that's basically how you're going to be doing all these problems in this chapter. Let's take a quick look at question number 6, make sure that we know what's going on here. Looks like it's basically the same thing as what happened in question number 5. Again, you're being asked to calculate the pooled variance, then find the estimated standard error, right? That's what you did up here, and then determine whether the treatment was significant or not. That's what you did right here. Okay, so with that, I'm going to go and move on to question number 7 then. And we'll say that first what I'm going to do is read the question. It's a pretty big, giant question here. So I'll read it so that we can get a sense of what's going on here. And then once I've done that, then we'll talk about how to solve this. First, let me just kind of know, this is the first question where we're saying, okay, here we're going to use all 4 steps of the hypothesis test, right? Step 1, 2, 3, and then step 4. How are we going to do it? First, let's read the question. It says, research results suggest a relationship between the TV viewing habits of a 5-year-old child or children and their future performance in high school. For example, these authors report that high school students who regularly watch Sesame Street as children had better grades in high school than their peers who did not watch Sesame Street. Suppose that a researcher intends to examine this phenomena using a sample of 20 high school students. The researcher first surveys the students' parents to obtain information on the family's TV viewing habits during the time that the students were 5 years old. Based on the survey results, the researcher selects a sample of n equals 10 students with a history of watching Sesame Street, and then a second sample of n equals 10 students. And this second sample now is going to be kids who did not watch Sesame Street. The average high school grade is recorded for each student, and the data are as follows, right? So here are your 2 groups. Those that watched the Sesame Street, those that did not watch Sesame Street when they were 5 years old. The numbers that you're looking at is for each group what their high school grade is. Okay, so here you got a bunch of different grades, and here you got a bunch of different grades. Question they're asking here is, are the grades for the kids who watch Sesame Street better than the grades of the kids who did not watch Sesame Street, right? So basically, are these scores higher than these scores? So with that, here they're asking the question, use an independent measures t-test with an alpha of 0.01 to determine whether there is a significant difference between the two types of high school student. Notice one thing that they're not doing here is they're not telling us how many tails to run in the study. So let's just assume that this is going to be a two-tailed test. Okay, so how do you go about conducting the hypothesis test? Let's talk about everything step by step. First is step one, where you state your two hypotheses, right? Your null hypothesis and your alternative hypothesis. Null is going to say that there is no difference between these two different groups. The way it's saying it is the population for the first group minus the population from the second group, right? Their two means is not going to be any different from each other, right? They're going to be the same, so their difference is going to be 0. Your second hypothesis, your hypothesis, or your alternative hypothesis, H sub 1 says the two groups are going to be different from each other. Their difference is not going to equal 0. Okay, so then step 2, you find that critical value, right? What's the number that you have to beat? How are we going to find that number? Remember, we have first what our alpha level is. It's 0.01. How many tails running? We said it was going to be 2. And we also have to remember how many degrees of freedom do we have. Here, we're saying that the way that we're figuring out the degrees of freedom, right, is n minus 1 for the first group and n minus 1 for the second group, and you add what's left, and that gives you the degrees of freedom. Both groups have 10 participants, right? That's what it says here. So it's 10 minus 1 plus 10 minus 1 gives you 18. So we go look that up. Right here I'm saying it's going to be 2.878. But how do we find that 2.878? We said first we're in the two tails column or row, and we're looking for the column 0.01. Then we're going to critical value 18. And that's where we're finding that 2.878. Okay, so that's the number that we have to beat, right? We have to, our t that we calculate has to be higher than this critical value for our treatment to be significant. So that's where step 3 comes in, right? We go do our 3 separate calculations. The 3 separate calculations are going to be, first we're going to find the pooled variance, then we're going to find the estimated standard of error, and then we're going to find the t. How do I find pooled variance first? It is 200 plus 160 over 9 plus 9. Remember, I'm getting that 200 and that 160. Remember, those are my two sums of squares. Where's that 9 plus 9 coming from? Right, remember, those are the 2 degrees of freedom from my two ends. Ends up giving me a pooled variance of 20. So then I'm going to use that to go calculate the estimated standard error. The estimate of the standard error. And it is the square root of 20 over 10 plus 20 over 10. It's going to end up giving me a pooled variance, a estimated standard error of 2. Now I'm going to use that to calculate t, and t is ending up going to be, my numerator is going to be 93 minus 85. Where's that 93 and 85 coming from? Remember, that's my mean of the first group minus the mean of the second group. And so it's going to be that over 2. Where's that 2 coming from? Remember, that's coming from my my estimated standard error. And so I end up getting a t of 4. That leads to step 4, where I'm deciding, is my treatment statistically significant or not? Remember, the crux of the decision is this value greater than this value? Here I'm saying that yes, 4 is greater than 2.878. So therefore I'm deciding to reject the null hypothesis. In rejecting the null hypothesis, I'm deciding that there's a significant difference in high school performance of users versus non-users, right? So people who watched Sesame Street versus people who did not watch Sesame Street. Okay, so that's everything for question number 7. I'm going to go ahead and move on to then take a quick look at question number 8. Looks like with question 8, it's basically the same kind of question, right? So you're given another situation, a bunch of data. The data is, again, where there's information about one group and then information about a second group. You're going to take that to answer question A, which is asking, is there a significant difference between the two different groups? Right, so for here, that's going to be where you're going to run your steps 1 through 4. Once you've done that, then you're going to move on to question B, and you're going to calculate this effect size thing, the Cohen's D. Now, this is something that we talked about in the chapter 10 lecture notes, and it's basically just this formula on the page 2 of the chapter 10 lecture notes. After that, then you're going to write a sentence demonstrating how the outcome, right? So basically you're going to write a sentence demonstrating how you would write your outcome in a research report. Remember that I showed you how to do this in your chapter 9 questions. So you want to go back to that and refer to those to get that answer. From there, though, I'm going to go ahead and move on to question number 9 from our lecture notes. Oh, no, sorry, question 9 from our odds probs. Sorry, I need to adjust my phone here. See if I can get all of this in. First, I'll read the question, and then I'll go over the answer. Here it says, does posting calorie content for menu items affect people's choices in fast food restaurants? Right, so basically they're asking, if people go to a fast food restaurant and they order food and there's calorie content information about the food shown, is that going to affect how people choose what to eat? According to results obtained by these authors, the answer is no. It's not going to affect how they choose to eat. The researchers monitored the calorie content of food purchases for children and adolescents in 4 large fast food chains before and after mandatory labeling. It began in New York City. Although most of the adolescents reported noticing the calorie labels, apparently the labels had no effect on their choices. Data similar to the results obtained show an average of, right, so here's a sample mean of 786 calories per meal with a standard deviation rate, a sample standard deviation for 100 kids and adolescents before the labeling, compared to now a second group, where the second group's mean was 772, their standard deviation was 91, and their N was 100. Use a two-tailed test with alpha equals 0.05 to determine whether the mean number of calories after the posting is significantly different than before calorie content was posted. Here, I guess I should just point out that anytime that you're being asked to find if there's a significant difference in something, right, and you're getting all this information about alpha levels and how many tails you're running, you should just automatically know by now that question means that you are going to be running steps 1 through 4. Okay, so real quick, just take a look at question B. Question B is saying calculate the R squared to measure the effect size, the mean difference. I'll talk about that when we get to it. So I'll just start about question A right now. Right, so question A wants to know, is there a significant effect of the treatment? We're going to go through steps 1 through 4 to get that question answered. And we'll start out with our step 1. Here we're saying that the null is that there is no difference between the two populations. The alternative is that there is a difference between the two populations. So we can just move on to step 2, where now we have to find out what our critical value is. Right, our alpha is 0.05. We're running a two-tailed test. Right, alpha 0.05 two-tailed test. Our degrees of freedom is 198. How am I getting 198? Remember, one group had 100 and the other group had 100. Right, so it's 200 participants total. Basically, you just add those up, minus 2. Right, so it's 200 minus 2. That's how I get that 198. So then I break out my T table, look it up, and I end up getting a critical value of 1.984, right? So that's my number that I need to beat. So let's go ahead and move on to our equations in step 3. I've got them laid out here. First, we just kind of want to notice that I have to do something funky to my equations. Right, so remember that what we always do is, in the equations, we always first calculate the pooled variance. Right, and the pooled variance requires this information: sum of squares and degrees of freedom. And the question here, the authors did not give us sum of squares information. They gave us degrees of freedom information, but no sum of squares information. So because I don't have any sum of squares information, I have to figure out what sum of squares are for group 1 and group 2. The only information that they gave us for this was the sample standard deviation for one group and the sample standard deviation for the other group. So I'm going to use those two sample standard deviations to figure out what the sum of squares are. How did I go about doing it? I'm just going to show how I did it one group at a time. Okay, so we're saying that I need to know what the sum of squares is for that first group. All I know about that first group is that their standard deviation is 85. Right, remember standard deviation, right? So S equals 85. Remember that when we used to calculate standard deviation and then like that sample standard deviation, we first had calculated our sample variance, right? All sample variances is the square of whatever your standard deviation is. So I'm on this road where I'm wanting to go from my sample standard deviation is to what my sum of squares is. To get here, I'm going to start here. I'm going to say, okay, I want to know first, what is the sample variance of this, right? All it is this 85 squared, right? It's that S squared. So what is that? That means that if my standard deviation is 85, the sum of variance of this group is 7,225. Why do I want to know this? This is why I want to know that is because remember, sample variance is gotten by calculating sum of squares over degrees of freedom. Right? So I'm going to use this equation to figure out what my sum of squares are. I know what my variance is. I just got it over here. I also know what my degrees of freedom are. It's this 99. The only thing I don't know is what my sum of squares value is. Right? So I created this equation where my sample variance is that 7,225 equals my sum of squares that I don't know over 99, my degrees of freedom. I'm going to use this to figure out what that sum of squares is. Right, so we do that fancy algebra that we've been talking about. Basically, you get the sum of squares by itself on one side of the equal sign by getting rid of the numbers that are associated with it. In this case, it was the 99, multiplied it out, multiplied it over here. So then I end up getting the sum of squares of 700,000, 15, and then 275. Right, so that's my sum of squares for my first sample. Remember what I need to do is now get the variance for my second sample, right? So I'm gonna do exactly the same thing. I know what my second sample's variance is because I know that second sample's standard deviation. All I'm gonna do is take that standard deviation, multiply it by itself. 91 times 91 gives me 8,281. With that, I'm going to figure out what my sum of squares is for this sample. Doing exactly the same thing I did over here. Ends up being 819,819. Kind of a weird number. But now I have my sum of squares 1 and my sum of squares 2. Because I have those two pieces of information, I can now go calculate my pooled variance, right? I've got my sum of squares 1 and my sum of squares 2. Okay, so I'm gonna go and do that. That's what I'm doing right here. Pooled variance equals that 715,275 plus the 819,819 over 99 plus 99 gives me a pool variance of 7,753. Now I'm going to use that pool variance to calculate the third thing, right? The estimated standard error. It's going to be this equation, right? That 7,753, that pool variance over 100. Why 100? Because it's the two n's right there. Gives me an estimated standard error of 12.45. Now I'm going to use that to calculate my t, right? The 12.45 is going to go in the denominator. The two means are going to go in the numerator, right? 786 minus 772, where am I getting that? That's this mean here and that mean there. So then it's going to give me a t of 1.12. Then we're comparing this to my critical value. It's smaller than my critical value. So my step 4 is that I'm going to decide to accept the null hypothesis. Okay, so that's everything for question number 9. Oh, actually there's one other thing that I'm supposed to do on the question number 9, right? So after we've done all this stuff for question A, with all of this, then there's question B, and it is where you're supposed to calculate the R squared for this problem, right? That's another effect size question. Where do you find R squared? If you go back to your chapter 10 lecture notes, remember it is this equation here, right? R squared equals t squared over t squared plus degrees of freedom. So real quick, I'll just do that. R squared then is going to be 1.12 squared over 1.12 squared plus my degrees of freedom, which is 198. Right, so that's going to give me then, it's going to give me 1.12 times 1.12. Gives me 1.25 over 1.25 plus 1.98. That's going to end up giving me, going to take care of that denominator. End up giving me, add the 108. It's going to give me 199.25. And that will reduce to 1.25 divided by 199.25 equals, is going to give me 6.27. There we go. Okay, so I'm going to go and move on to the next problem from there, and that is a quick look at number 10. Here I'll just kind of know, looks like it's the same kind of thing, given data about two different groups. We also asked, are they just significantly different from each other? So that's going to be your steps 1 through 4. Question B is where you're going to calculate components D. Right? Remember that is in your chapter 10 lecture notes. There's your Cohen's D formula right there. And then question C, you're going to just write a sentence where you're articulating what your results are. I'm going to go ahead and move on to question number 11 from there. Got another long one here. I think what I'll do here is I'm just going to go ahead and let you read all of this part on your own and just kind of cut to the chase with what are they asking us to do in the work. Right, so if we go to question A, basically what they're asking us to do, again, is to take the two groups and run the hypothesis test. How we know that? We know it because they're asking us to run a one-tailed test with an alpha of 0.05. Okay, so we'll just say that to start off with, the hypothesis statement is going to read, here I'm calling it mu H is going to equal mu L. What am I meaning mu H and mu L? That's what I mean here by high creativity participants and the low creativity participants. Basically, remember the null is that the two are going to equal each other. Here, the high creativity participants are going to equal the low creativity participants. Here, I'm kind of writing a new type of alternative hypothesis. Right, the prediction is that the two groups are going to be different from each other. But here, I'm predicting what the difference is going to look like. Here, I'm saying the population of the low creativity group is going to be smaller than the population of the high creativity group. Why am I doing that? I'm doing it because we're running a one-tailed test, right? With a one-tailed test, remember, we're predicting if the two groups are different from each other, what's the direction of the difference going to be? Okay, so with that leads to step 2, where we go to find our critical value. I'll just note that the information that we were given was we have a, oh shoot, I'm just noticing that I made a mistake here. I ran it as a 0.05, but I thought it was a two-tailed test when it was actually a one-tailed test. So this critical value may not be right. Degrees of freedom is right. It's still going to be 52. How do we know that? We know that because it's going to be 27 plus 27, and that is what, like 54, right? So take a participant out of here, participant out of there, it's going to be minus 2. 54 minus 2 is 52. So let's just go real quick to see what our critical value is here. That it's a 0.05 one-tailed test with degrees of freedom of 52. Okay, so one-tailed test. That's my 0.05 column. Going to degrees of freedom of 52. I don't see a 52 in here. I see a, what is that? A 40 and a 60. So I'm going to go to the 40. That's the more conservative one. I'm going to say that then the t value that I'm going to be using as my comparison value, it's going to be this 1.684. Oh, looks like that is what I did have before, 1.684. I just wrote the tails down wrong. It's a one-tail test. Okay, but that's the number that we're going to be, 1.684. How are we going to do it? We're going to do our series of 3 calculations. Right, first we're going to calculate our pooled variance. It's the sum of squares 1 over the sum of squares 2, or plus sum of squares 2. Right, that's this sum of squares plus that sum of squares right there. Over, there are 2 degrees of freedom, 26 for each because our ends were 27. That gives us a pooled variance of 30.375. That then gets used as our numerator in our 2 fractions here. Notice that we've got 27 in our 2 denominators because this is the 2 ends. But that gives us an estimated standard error of 1.5. We use that in our denominator for our t equation, right? And that's 7.41 minus 4.78. When we're getting those 2 numbers, that's the mean of the first group minus the mean of the second group. gives us a t-value of 1.75. What did we have to beat? We had to beat 1.684. So because we did beat it, right, this is 1.75 is greater than 1.68, we can conclude that we can reject our null hypothesis. We're not done with our work over here, though, right? We have to move to question B, where we go calculate Cohen's D. That's what we did here. Let's just say we ended up with a Cohen's D of 0.47. From there, though, I need to move on to my statement. I think I actually wrote it out this time. How am I going to write out this statement? Right, the way that would look is, we'll say, high creativity people are significantly more likely to cheat than low creativity people, comma, and then here, right, this all is saying what your T is. Remember, we here's saying this T is 1.75 because that's the T that we got down here. What is that 52 in those parentheses right there? Remember, that is your degrees of freedom that we calculated earlier, right? So T parentheses degrees of freedom equals 1.75. Remember, this is our probability that we ran the test out, the one-tail test. Oh, there I got it right, one-tail test. And then your D, 0.47, that's this D down here that we got, okay? So that's what this statement should look like. Let's go move on to the next problem. The next problem is going to be 12. Just take a quick look at that. Well, you're just being asked one question here. For these two groups, run the steps 1 through 4 with this being your alpha level and that being the number of tails. So with that, we can go ahead and move on to question number 13. Right here we'll say for question number 13, I'll go ahead and read the whole question to you guys this time. Says that McAllister et al. Compared varsity football and hockey players with varsity athletes from non-contact sports to determine whether exposure to head impacts during one season have an impact on cognitive performance. The study, tests of new learning performance were significantly poorer for the contact sport athletes compared to the non-contact sport athletes. The following table presents data similar to the results obtained in the study. Right, so basically what they're saying here is, were these athletes significantly different from these athletes in terms of cognitive performance? Right? The idea is that the contact athletes, because they had contact, like they might have had more head injuries, so they're going to have less or not as good cognitive performance as these athletes are going to have. Okay, so basically we're supposed to run the whole hypothesis test, steps 1 through 4. Right, that's this question A here. Are the two significantly different from each other? But now, one-tail test at alpha 0.05. Notice that when they ask the one-tail test, they're not just asking are the two groups different from each other. Now, remember, it's the predicting the direction of difference. The direction of difference here is that the contact sport athletes are going to be lower than the non-contact athlete sports. Right? That's the one-tail test that's being run there. Okay, so let's just take a quick look at everything we had to do. Step 1 was where you made your prediction. The null said that the two groups were not going to be different from each other. The alternative hypothesis said that the two groups are going to be different from each other. And because we ran the one-tail test, we're identifying what the difference is going to be. The difference is that the contact athletes are going to be lower than the non-contact athletes. So step 2 was we had to go find out what our degrees of freedom were going to be. Here we're saying that for running an alpha level of 0.05 with a one-tail test, our degrees of freedom is going to be 14. Where are we getting that 14 from? We're getting that 14 from the groups. We're saying that here for this group we had an N of 8. Here for this group we had an N of 8. The degrees of freedom are 7 here and 7 there. Right, so that 7 plus 7 gives us that 14. So we have a critical value of 1.761. Okay, so this is all the information they gave us to go do our significance level test. Remember, what we're supposed to do is first calculate that pooled variance. But what did I have to do to go calculate pooled variance? Remember, we have to first go get your sum of squares for this group and sum of squares for this group. So I had to go and do all the math, right? This is all chapter 4 stuff. What was the sum of squares for this group, and what was the sum of squares for this group? Remember, the way they did it from chapter 4 was first we went and found each group's sum, their n, and then their average. And then we also had to go and calculate the computational formula. So for each sample, we also had to find out what each sample's sum of x squared was. And that's how I ended up getting the sum of squares of 44 for this group and the sum of squares of 56 for this group. Okay, so got all that information, led to a step 3, right? Step 3 is, first I'm going to calculate the pool variance, then I'm going to calculate the estimated standard error, then I'm going to calculate t. So for pooled variance, it's 44 plus 56, right? The 44 plus the 56 over my degrees of freedom, because I have an n 8 there and an n 8 there. It's 7 plus 7, gives me a pooled variance of 7.14. Take that pooled variance, use it to calculate the estimated standard error, right? So that's what that equation looks like. Gives me a value of 1.33. That, because my denominator of my t equation, where it's 9 minus 6, we're getting that 9 and that 6. That's that 9 minus that 6. I end up getting a t of 2.25. Remember, my critical value was 1.761. So my step 4 was to decide whether to accept the null or reject the null. Because my t that I calculated was greater than my critical value, I decided to reject the null and decide that my findings were significant. Question B is asking to calculate r squared, right? So I ended up getting with r squared of 0.265. Okay, so I'm going to go and move on to question number 14. Here, we're saying that basically you're doing exactly the same thing. You're given some information about one sample and another sample. Question A is we're supposed to find out, is there a significant difference between the two samples? And then question B is just calculate Cohen's D. Where Cohen's D is that formula. Okay, so then it's going to move on to question 15. And we'll say that, I'm just going to run you through this really quickly. Question 15 is asking, is this group significantly different from this group? Right, that's your question A here. You are running a two-tailed test with alpha of 0.05. So there is your step 1, your null hypothesis versus your alternative hypothesis. There is your step 2, where you're finding your critical value. How did I get that critical value? Alpha of 0.05 with two-tailed tests, and my degrees of point being 14. How am I getting that degrees of 14? N of 8 and N of 8. Step 3 is to calculate first the pool variance, then the estimated standard error, then the t. I've got a 16 for my pool variance. Leads to a 2 for my estimated standard error, which then leads to a 2.17 for my t. Remember, my critical value was 2.145, so because 2.17 is greater than 2.145, I can go ahead and reject my null hypothesis. By the way, here's some interesting information about solving the questions being asked about over here. Before we end this, though, just note that there is a question B here, right? It's supposed to calculate a confidence interval. This is the generic formula for calculating the confidence interval. Remember, I did explain it in the end of your chapter 10 lecture notes here. So let's just kind of run through this real fast. When you go to the confidence interval, remember what you're doing is you're solving for this expression here, mu1 minus mu2. What you're going to do is you're going to end up getting two values for this. I'll just note that it's going to be a value here and a value here. How am I getting those two values? First, you're noting that in your formula, whereas you're solving for this, right? You're solving for this, you're using numbers that you're being given. What's the first number that I'm being given? First number I'm being given is this difference here. Right, that difference was this difference here. I didn't note it when I solved it, but it is 10.5 minus 6.16, which gives me a value of 4.34. That is plus or minus your t value. How do I know what my t is? Here I'm saying my t is 1.761. How did I get that 1.761? The way you're supposed to find it is you go to your t table and you look up your t value based on whatever your confidence interval is. So here it's a 90%. And so you find that 90% here and you find a t value in there based on whatever your degrees of freedom are. Remember, my degrees of freedom are 14. So I go to my confidence interval of 90%, degrees of freedom of 14, and I use the t that I find there. That's this 1.761. So that 1.761 for that t is multiplied by your estimated standard error. Remember, we figured that that was 2, so it becomes that 1.761 times 2. Okay, so what I'm going to do is I'm going to take this 4.34 and I'm going to add it to what these two things multiply to, and that's how I get this 7.862. Also, though, going to take this 4.34 and I'm going to subtract it from whatever this multiplies to. And that's going to give me that 0.818. And that's how I have the two values for what my confidence interval is. Okay, so that's all I'm going to give you for question 15. I'll just note that there also is a question 16 for this. The question reads, researcher conducts independent measures study comparing two treatments and reports the t statistic as t, where your degrees from 25 equals 2.071. First question that's being asked here is question A, how many individuals participated in the entire study? The way that you're able to answer this question is by looking at the degrees of freedom that are giving you in the information of the question. Remember, degrees of freedom are your n minus 1, your n minus n1 minus 1 plus n2 minus 1. So what that means is that I must have had 27 participants in the study, right? Because it's your n minus 2, basically, right? So what must have happened here was in this study, I must have had a group where one was 13 and the other group, so one n was 13 and the other group, their n was 14. Okay, so that's how you answer question number 8. I'll let you figure out how to answer questions B and C on your own. And from there, we'll call it a lesson. Thank you very much.